Hello everyone, welcome to this lecture series in linear algebra. Today we are going to talk about orthogonal sets, orthogonal projection and the Gram Schmidt process. As we have already discussed in the last lecture, the orthogonal vectors, that means if you have two vectors u and v, they are orthogonal if their dot product or inner product is 0. So now what are orthogonal sets? So orthogonal sets, a set of vectors u1, u2, up in Rn space, okay, they are in Rn space means that each vector has n elements, okay, is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal, okay. That means if you take any two distinct vectors from the set, they are orthogonal. That means their inner product or dot product is exactly 0, okay. So that is if ui dot product with uj is 0 whenever I is not equal to j, means ui and uj are two distinct vectors from this set. So for example, whether this set of three vectors u1, u2, u3 is orthogonal where these three vectors are given. So to check whether this set is orthogonal, we have to take each pair of distinct vectors from this set and check whether their dot product is 0 or not, okay. So there are three vectors, so there will be three pairs, okay, u1 paired with u2, u1 pair with u3 and u2 pair with u3, and u1 dot u2 and u2 dot u1 is same because of the property of inner product, okay. So we just need to check the u1 dot product with u3 whether it is 0 or not, u2 dot product with u3 and u1 dot product with u3, okay. So these are the three pairs u1 dot u2, okay. So this u1 vector when taken dot product with u2, so that means corresponding elements will be multiplied and they are added, okay. So 3 multiplied minus 1 plus 1 times 2 plus 1 times 1, okay. So you can clearly see that this sum is 0. Similarly, dot product of u1 with u3 is 0 and dot product of u2 with u3 is also 0. So each pair of vectors are orthogonal, so the set is a orthogonal set, okay. So clearly this set of three vectors is a orthogonal set. Now the orthogonal basis of a subspace, okay. So an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set, okay. So by a basis means a linearly independent set that spans the subspace, okay. So if you have a orthogonal set such that the vectors are linear independent and they span whole of the W space, then it automatically becomes a orthogonal basis, okay. So this result is very useful in the sense that if we have to find any vector in terms of basis, we used to write that vector as a linear combination and we need to find out the constants by solving the non-homogeneous solution, okay. But by now this theorem will help us finding those constants immediately without actually solving the non-homogeneous system using the augmented matrix. So here's the theorem that let you have a orthogonal basis for the subspace W for Rn, and because the orthogonal basis for W, then if you have any vector in W, that can be written as a linear combination. This we already know. So for each vector y in W, there exist weights C1, C2, Cp such that y can be written as a linear combination of these vectors because these vectors span W. So any vector in W has a linear combination with these vectors. And now you can see that this is a non-homogeneous system of equations, and usually we used to find these weights by solving the augmented matrix and finding the solution of that, okay. But if the set of if this basis is orthogonal, then these weights can be directly calculated by this formula that the Cj weight can be calculated as the inner product of y with uj divided by the length square of uj dot uj, okay. And this is true for any j1 to p, that means we can calculate c1 c2 up to cp, all the constants. The proof of this is very simple, that let there be weights C1, C2, Cp such that y in W is written as a linear combination of the basis vectors. So we can always write this with unique weights. Okay, we have already discussed this. Now the question is how to calculate this. So to calculate this, if I calculate the dot product of y with the uj element, then that will be same as the dot product of this linear combination with the uj vector. And by uh, property or linearity, we can write it as c1 times u1 dot uj plus c2 times u2 dot uj plus so on. And because they are orthogonal, so only uj dot uj will be non-zero and other dot products will be exactly zero. Okay, so we use that orthogonality of these vectors. That means any pair of vector, if I take distinct vector, their dot product is zero. And if I calculate y dot uj, so it will be this linear combination times uj, and it will give only cj times uj dot uj, because dot product of this jth vector with first, second and so on with any other vector except jth vector will be exactly 0 due to orthogonality. So we can calculate cj because uj dot uj is a non-zero number. Okay, because this is 0, then uj has to be 0 vector, and because they are in basis, so they are non-zero vectors. So uj dot uj has to be a non-zero number, so we can divide with this. So and we can calculate cj as y dot uj divided by uj dot uj. Okay, okay, remember this is not 0. Okay, because they are in basis, so they have to be linearly independent. Okay, so this dot product has to be non-zero. If this dot product is 0, then uj is itself a 0 vector, and so base it cannot be basis, it becomes a dependent set. So right, so that means if you have a orthogonal basis, then you can write any vector as a linear combination and calculate the weights easily by this formula. Okay, say for example, say S is a orthogonal basis for R3. Okay, exactly 3 vectors, and each vector is in R3, so having 3 elements, of course. Express the vector y as a linear combination of vectors in S. Okay, so given u1, u2, u3, these 3 vectors, which is a basis for R3, so that means they are linearly independent vector and they are going to span whole of R3. So if you take any vector in R3, we can write it as a linear combination of u1, u2, u3 with some weights c1, c2, c3, and those weights are unique. Okay, so we have to find those c1, c2, c3. Okay, and because they are orthogonal bases, so we can calculate these weights directly without solving the augmented matrix and finding the solution of this non-homogeneous system. Okay, so the weight c1 we can calculate as y dot u1 divided by u1 dot u1. C2 will be y dot u2 divided by u2 dot u2, and C3 will be y dot u3 divided by u3 dot u3. So basically we need to find this dot product of this y vector with each of u1, u2 and u3. So you can calculate y dot u1. Okay, so that will be 18 plus 1, 19 minus 8. Okay, so we immediately get that value. And also we need u1 dot u2 u1, so that means length of u1 squared, length of u2 squared, and length of u3 squared. So square of these adding. Okay, so for cj's we can calculate by this, and for that we need the y dot product with u1, u2 and u3. So you can calculate y dot u1 as 11, y dot u2 as minus 12, so that you can see minus 6 plus 2 minus 8, so minus 14 plus 2 is minus 12. Y dot u3, so you can take dot product u1 dot u1, so that's 3 square plus 1 plus 1, so 9 plus 2 11, and 1 plus 4 plus 1, so 6. Okay, and then square of this plus square of this plus square of this is u3 dot u3. And so you can calculate c1 will be y dot u1 divided by u1 dot u1, so 11 by 11, which is 1. Y dot u2 divided by u2 dot u2 will be c2, so minus 12 by 6 is minus 2, and y dot u3 minus 33 divided by this 33 by 2, so again that is minus 2. So clearly y can be written as a linear combination of u1, u2, u3 with these weights. So we have the equation, or we have the linear combination, that y is first vector minus 2 times second vector minus 2 times third vector. Now take the second definition, which is orthogonal projection. Okay, so it says that given a non-zero vector u in the Rn space, consider the problem of decomposing a vector y in the Rn space into sum of two vectors, one a multiple of u and other orthogonal to u. Okay, so consider that in the Rn space you are given a vector u, and the problem is to decompose another vector y as sum of two vectors, one in the direction of u and other perpendicular to the direction of u. So that means the other in this direction. Okay, so we are trying to decompose this y in the direction of u and one in the perpendicular to u. So that means this y can be decomposed as y cap plus z, where y cap is in the direction of u, so y cap is a scalar multiple of u, and z is perpendicular to u vector. Okay, so clearly y, if I writing it as or decomposing it as sum of two vectors y cap and z, where y cap is in the direction of u, so y cap can be written as a scalar times u. Okay, and z is orthogonal to u. Okay, so z is orthogonal to u means the dot product of z with u will be exactly 0. Okay, so they are perpendicular. Now since from here if I calculate z vector, then it will be y minus y cap. Okay, and y cap we are saying it is in the direction of u and it can be written as alpha times u, so I can substitute y cap as alpha times u. Okay, so z will be y minus alpha times u, and because z is orthogonal to u, so this vector orthogonal to u means that the dot product of z with u is exactly 0. So if I substitute the z value here as y minus alpha u, then that means y minus alpha u dot product with u equal to 0, and from here I can calculate this alpha. Okay, so immediately 0 equals z dot u and z is y minus alpha times u. So I can solve this as y dot u minus alpha times u dot u, and because u is a non-zero vector, so u dot u is also non-zero, so I can easily calculate alpha as y dot u divided by u dot u. Okay, so this is the value of the scalar. So immediately once we have the scalar, we have the y cap. Okay, so we have the projection of y in the direction of u y cap as alpha times u. Okay, so y cap we can calculate alpha u, and alpha is this, so we immediately get y dot u over u dot u times u, and it is the projection of y in the direction of u, so we can write it as projection y onto u. Okay, so this is the symbol projection y onto u or y cap, which is calculated as this value. Okay, so the vector y cap is called the orthogonal projection of y onto u and is written as projection of y onto u, and vector z, which is the perpendicular vector, it can be calculated as y minus y cap. Okay, and it is the orthogonal to u vector. So if you are given any vector and we want to find the projection along u and a perpendicular vector, then first we can calculate the projection y cap using this formula. Okay, and once we have this, then we can find the perpendicular vector z as y minus y cap. Okay, y is already there and y cap we have calculated, so we can calculate the perpendicular vector as well. So this is the concept of orthogonal projection. Okay, so let us take one theorem and then we will take example on this. The orthogonal decomposition theorem. Okay, so let W be a subspace of Rn, then each vector y in the Rn space can be uniquely written in the form y as y cap plus z, where y cap is in the space W and z is in the W perpendicular space. Okay, so this theorem says that if you have a vector y, and if we want to find its projection on a subspace W, then we can find it and we can write that y is y cap plus z, where y cap is the projection of y on the subspace W. Okay, so it is the projection of y on the subspace W, and z is the orthogonal vector to this y cap. Okay, so z belongs to W perpendicular because z vector will be perpendicular to every vector in the on this subspace, so z belongs to W perpendicular space. And In fact, if you know the basis of this subspace, and if you have that u1, u2, up is a orthogonal basis of w, then this y cap can be written as linear combination of that basis, and we know that the weights c1, c2, cp can be calculated by these formulas, okay, because they are orthogonal basis. So we already did this in the previous slides, that the if I write any vector as a linear combination of orthogonal basis, then the weights can be calculated easily by these formulas, okay. And once we have y cap written as this, then z is the perpendicular vector which can be calculated as y minus y cap, okay. So we can easily write y projection on the W space as y cap, which is a linear combination of what, of all the projections, okay. This if you see, then it is the projection of y on u1, okay. This is the projection of y onto u2, and this is the projection of y onto up. So if you know the basis, then y cap, which is the projection of y on W space, is nothing but sum of projections on the basis elements, okay. And then we can calculate the vector perpendicular to the subspace W as y minus y cap. So what we need to prove here is that if I write y cap as a linear combination of this, then y cap belongs to W, and then if I calculate z as this, then z belongs to W perpendicular, and then this decomposition is unique, okay. So we are going to prove these three things here. So to start with, let this u1, u2, up be orthogonal basis to W, okay, and let us define that y cap is defined as given by this equation, okay. So let this be a basis for W, and let y cap be a linear combination of this. So this is sufficient to prove that y cap belongs to the W, because if these vectors span all of W, and if any vector can be written as a linear combination of bases, then that vector also belongs to that space, okay. So y cap belongs to W, that's one thing. Second, we have to prove that z belongs to the W perpendicular. That means z is perpendicular to each vector on the subspace. So if we prove that z is perpendicular to every vector in the basis, then automatically because every vector in W space is a linear combination of this, then z will be perpendicular to every vector of W. So if I calculate z dot product with u1, okay, so that's the first step. So z dot product with u1, and z is y minus y cap, so it is y minus y cap dot product with u1, so it is y dot u1 minus y cap dot u1, and y cap is this linear combination. So this linear combination dot product with u1 will only give the first vector here, u1 dot u1 will be non-zero, and u2 dot u1, u3 dot u1, and up dot u1, they will be all zeros. So the rest all will become zero, only the first will give value. So y dot u1 and y cap dot u1 will be only this, u1 dot u1 will give value. So this u1 dot u1 will cancel out, and y dot u1 minus y dot u1 will be exactly 0. That means z is perpendicular to the u1 vector. Similarly, if I calculate z dot product with u2, so again with the similar process we'll get that it is 0, okay, and so on we can do with every vector in the basis. And so each pair of z dot product with each vector of uj of the basis is exactly 0, okay. So here we have solved that z is orthogonal to u1. Similarly, you can prove that z is orthogonal to every vector in the basis of W, and so in general z is orthogonal to every vector in the whole space W, okay. And if it is true, then z belongs to the perpendicular set, okay. So z belongs to W perpendicular. Now the third thing we need to prove is that the decomposition y is equal to y cap plus z is unique, okay. So let, if possible, there are two decompositions. Y can be written as y cap plus z, and y can also be written as y1 cap plus z1, where y cap belongs to W and z belongs to W perpendicular, and so y1 cap belongs to W and z1 belongs to W perpendicular space. So because y can be written as this as well as this, so these two must be equal, okay. So y cap plus z must be equal to y1 cap plus z1, and so we can take y1 to other side and z to the second side. Okay, so we can rewrite this as this equation. Now both these vectors are in w. Okay, so this difference is also in w, and both these vectors are in w perpendicular, so difference is also in w perpendicular, because we know that if w is a subspace, then w perpendicular is also a subspace of Rn. So if I call this difference as a v vector, okay, if I call v vector as this difference, then this v vector belongs to the w space. And if I am writing this difference as v, then automatically this difference z1 minus z is also v. So because z1 minus z belongs to w perpendicular, so v also belongs to w perpendicular. Now we know that if any vector belongs to w as well as w perpendicular, then that vector has to be zero vector, because the dot product of this v vector with itself will be zero. Okay, so this implies v dot v is zero, implies v has to be the zero vector. Okay, and if v is a zero vector, then immediately we have that y minus y1 is 0, means y must be equal to y1, and then immediately we have z must be equal to z1. Okay, so y cap must be equal to y1 cap, and z must be equal to z1. That means this representation is unique. Okay, so this was your theorem. Now let us take one example here, that let y be a vector and u be another vector. Find the orthogonal projection of y onto u. Okay, so we have to find the projection of y in the direction of u. Okay, that means we want to calculate y cap, or we want to calculate y cap, which is alpha times u, and alpha we know what scalar, we have to find y dot u by u dot u. Then write y as sum of two orthogonal vectors. One is span of u, so that's y cap, and one in orthogonal to u. Okay, that is the z vector, which is y minus y cap. Okay, so what we need is y dot product with u and u dot u. Okay, so y dot product u you can calculate easily. Okay, u dot u we can calculate, and then we can calculate this y cap vector as alpha u, where alpha is this dot product by this dot product. Okay, so that's the orthogonal projection of y onto u is y cap, which is y dot u by u dot u times u vector. Okay, so these values we can substitute. U vector is 4 2. Okay, so immediately we have this y cap, okay, which is alpha, this scalar times u, so it is the span of u, and so it is the orthogonal projection of y onto u. Okay, the second we have to find is the vector orthogonal to u, perpendicular to u. Okay, so that is the z vector, which can be calculated as y minus y cap. Okay, so this vector minus this vector. Okay, so y minus y cap. Okay, so easily we can calculate this difference. Okay, and this vector is orthogonal to the u vector, and y cap and u vector are parallel in the same direction, so y minus y cap will be orthogonal to y cap. Okay, so that means you can check that dot product of these two vectors is exactly 0. Okay, clearly y minus y cap is orthogonal to y cap or the u vector, because they are in the same direction. Okay, say another example, let u1 and u2 are two vectors, and y is another vector, and w is span of u1 u2. Okay, so w is span of these two vectors. Write y as sum of vectors in w and a vector orthogonal to w. Okay, so we need to find the projection of y on the space w. Okay, and we have to find the orthogonal vector. Okay, so y cap and z, we have to write y as sum of vectors y cap and z, where y cap belongs to w, so that means y cap will be written as a linear combination of u1 u2, and the z vector is then orthogonal vector, which is y minus y cap. And because we are taking it on subspace, then it is also same as writing y cap will be projection of y1 on u1 plus projection of y on u2. Okay, so the orthogonal projection of y on the w space is same as the y cap, which will be now the projection of y on u1 plus projection of y on u2. Okay, so this is the projection of y on u1 formula plus projection of y on u2. And so we need to know what is y dot u1. So you can easily take the dot product of these two. 2 plus 10 12 minus 3, okay, 9, divided by u1 dot u1, so that's 4 plus 21 25 plus 1, okay, so that's 30. And u1 is the vector 2 5 minus 1. Y dot u2, so the dot product of these two, minus 2 plus 3, so we get 3. And u2 dot u2, so square of this plus square, okay, so 4 plus 1, so that's 6, minus 2 1 1 vector. So we can solve this and we can find this vector, okay. So this is the projection of y vector on the space w, okay. Now the perpendicular vector will be the z vector, which will be simply y vector minus y cap, okay, so this minus this. So see, y minus y cap, it gives us the z vector which is orthogonal to this space w, okay. So 1 2 3 minus this vector. So clearly you can see that these two are orthogonal, okay. So the product of these two will be 0, okay. Let's see, minus 14 by 25 plus 0 plus 14 by 25, exactly 0, okay. So this was another uh, result, okay. And so decomposition of y as sum of two vectors, so these are the two vectors, so we can write this vector y 1 2 3 as sum of y cap plus z, okay. One in as a projection in w space and other in the perpendicular direction. Now we take another definition here, the orthonormal set, okay. So a set of vectors is orthonormal set if it is orthogonal set of unit vectors. So the set is orthonormal if it is first orthogonal and the vectors are unit vectors. That means each pair of vectors has the inner product 0, okay, when we take two distinct vectors every pair. And each vector is of length 1, okay, unit vector. So each vector norm is 1 for every I, okay. So if these two properties are satisfied, then this set becomes orthonormal set. Now there is a one result here, okay. So if you are given a m cross n matrix U having orthonormal columns, then this result hold that U transpose U is identity, okay. So a matrix M cross N will have orthonormal columns if and only if U transpose U is I, okay. So clearly if U has orthonormal columns, then the column say u1 u2 up, okay. And if I take transpose and multiply with u, then diagonal elements will be u1 dot u1 u2 u2 up dot up, which are 1 1 1, okay, because length is 1, and non-diagonal elements will end up with a pair of distinct vectors, so they will end up with 0, so it gives us a identity matrix. Anyway, so we'll use it to write one result here, let U be a m cross n matrix of orthonormal columns, okay. So columns are orthonormal means that the each pair of distinct columns, their dot product is 0, and each column, if I calculate norm, it is 1. And let xy be any vectors in Rn space, then the length of ux is same as length of x. That means if I use the matrix of transformation as the orthonormal matrix, then the uh, length is preserved, okay. So for length of x vector do not change after transformation, okay. The transformed vector also has the same length as the original vector length. Second, the uh, ux dot product with uy, okay. So transformed vector of x dot product of with transformed vector of y is same as the dot product of the original vectors x and y. And also if the left hand side is 0, if and only if right hand side is 0, okay. So if dot product of transformed vector is 0, if and only if the dot product of the original vectors are 0. That means if this means that they are orthogonal, okay. So if you have two perpendicular vectors, then their transformation is also perpendicular, okay. So orthogonality is also preserved, okay. So if you have matrix of transformation as orthonormal matrix, then the lengths are preserved and orthogonality is also preserved. Proof of these are very simple, that for first, if you calculate the square of transformed length or norm of ux square, then we know it is ux times ux, and we know how to calculate dot product, the transpose of first times second, and AB whole transpose is B transpose A transpose, so it will give X transpose times U transpose, and by property U transpose U is I, so X transpose X, and that is norm X square, so lengths are preserved. Similarly, for second, if I calculate ux dot uy, then again the dot product means that the first transpose and then multiplied second, and again it is x transpose u transpose, but u transpose u is identity, so it is x transpose y, and that gives equal to x dot y. Okay, the third is obviously true. If left hand side is 0, then right hand side must be 0. Okay, now we'll give a very famous result, the Gram Schmidt process, and this process is used to produce an orthogonal or orthonormal basis for any subspace of Rn when you know one of the bases of that subspace. Okay, so if you are given any basis, okay, say x1, x2, xp is any basis for the subspace W of Rn, then we have to find, say, first orthogonal basis for this subspace W. So how we can do that? Okay, so to produce an orthogonal basis from any basis, what we do is we take the first vector of the given basis in the orthogonal basis. So we take v1 equal to x1, where v1 is now a new vector in the orthogonal basis. Okay, then we will write the second vector v2 using the x2 vector as v2 equal to x2 minus x2 projection on the first vector. Okay, first calculated vector. Okay, so and we know that projection of x2 on v1 is x2 dot v1 over v1 dot v1 times v1, so this with this definition. Okay, and so you can easily check that this v1 dot v2 is exactly 0. Okay, so if you multiply this v2 vector with v1, then you will get here x2 dot v1, here v1 dot v1, and v1 dot v1 cancels out, and we get x2 dot v1 minus x2 dot v1 as exactly 0. Or we just said that we can decompose any vector as sum of two vectors, one in the direction of u and other in the perpendicular direction. Okay, so we can calculate y cap and z. So here v2 is nothing but written as a z vector. Okay, if I call this x2 as y vector, then you can see that this is y vector, this is the projection, this is y cap. So this difference is nothing but the z vector. That definition on previous slides works here. Okay, now if we have to calculate the third vector, okay, so what is v3? V3 will be calculated from the third vector here, so we will write v3 as x3 minus projection of x3 on the previous calculated vector. So we'll write v3 as x3 minus projection of x3 on v1 minus projection of x3 on v2, and we know the formula for this. Okay, similarly, we have to calculate v4 from the fourth vector here, x4, then v4 will be x4 minus projection of x4 on the previous calculated these three vectors v1, v2 and v3. Okay, so if we have to calculate fourth vector v4, it will be the fourth vector of this set x4 minus projection of the x4 on v1 minus projection of x4 on v2 minus projection of x4 on v3, and we know the formulas for this projection. It is x4 dot v3 by v3 dot v3 into v3. Okay, similarly projection of x4 on v2 is x4 dot v2 divided by v2 dot v2 into v2. Okay, so you see this formula. Similarly projection of x4 on v1 is x4 dot v1 divided by v1 dot v1 into v1. Okay, so this, so and so on. We can continue this for the number of vectors in the basis. Okay, so if there are n vectors, we can calculate n orthogonal vectors. Okay, so these vectors which are produced here, they are orthogonal. That means if you calculate the dot product of any two distinct vectors, you will find that their dot product is exactly 0. Okay, So this process can be continued to calculate all the vectors. Okay, so because this is a basis, and if there are p vectors here for w, then exactly p vectors will form the basis with v1 v2 vp. Okay, the then this you can continue and calculate v1 v2 vp, which will be orthogonal basis for w. Okay, so that means they are linearly independent, they will span w, and each pair of distinct vector, their inner product is exactly 0. uh, uh, and also in addition, this holds that span of v1 v2 vk is same as span of x1 x2 xk for k1 to p. That means the span of x1 and span of v1 is just same. Similarly, span of x1 x2 is same as span of v1 v2. Also, the span of first three vectors x1 x2 x3 will be same as span of first three vector v1 v2 v3, and so on. Okay, and so this gives us the orthogonal basis. If we need to find the orthonormal basis, then we just need to normalize these vectors. Normalizing these vectors means dividing these vectors with their lengths. So if I calculate v1 divided by length v1, v2 divided by length v2, so on vp divided by length vp, then that set will be a orthonormal basis for w. Okay, so we can easily normalize to find the orthonormal basis from here. So now let us take say example here to show you how to do this. Let W be span of two vectors where x1 is this and x2 is second vector. Construct a orthogonal basis v1 v2 for W. Okay, so W is a span of these two vectors, and if these two vectors are independent, then these two vectors becomes basis for W. Okay, and clearly you can see that these two vectors are independent. Okay, and they are not orthogonal. If you calculate x1 dot x2, the dot product is non-zero. Okay, so they are not orthogonal. Say, so x1 x2 forms a basis for W, but not a orthogonal basis. Now how to construct orthogonal basis is that you choose the first vector x1 as v1. Okay, so we simply write v1 as x1, that means 360. Okay, v1 is 360, and now we just want to calculate another vector which is perpendicular to this and lying on the same space. Okay, so uh, v2 we will calculate from x2 as x2 minus projection of x2 on the v1 vector. Okay, so v2 will be x2 minus projection of x2 on v1, by formula this is x2 dot v1 divided by v1 dot v1 times v1. Okay, so x2 is given 1 2 2, x2 dot v1. Okay, so the dot product of these two, or dot product of these two, so 3 plus 12 plus 0, so that's 15. Okay, numerator, denominator v1 dot v1, so that's square and add, so 9 plus 36 45, and v1 360. So immediately we can calculate this difference. So this is the second vector. Clearly you can see that v1 dot v2 is 0. Okay, so the inner product of these two vectors is exactly 0. So they are orthogonal vectors, and they are independent, and they will span the same space as spanned by x1 x2, that means W. Okay, so they become the orthogonal basis for W. Okay, so v1 v2 is a orthogonal set of non-zero vectors in W, and they will form the basis for W. Okay, now take one more example here. Let x1 x2 x3 be three vectors, and the set of these three vectors is a basis for a subspace W of R4. Clearly these vectors are in R4, and these three vectors do not span whole of R4, they just span a subspace W of R4. Okay, now we have to construct a orthogonal basis for W. Okay, so if we have to construct this orthogonal basis for W, what we have to do is take first vector as v1. Okay, so we start with v1 as x1, where x1 is given. Okay, the second vector v2 will construct from x2 as x2 minus projection of x2 on this first vector. Okay, so v2 will be x2 minus projection of x2 on v1. So again the formula is this. So x2 is this vector 0 1 1 1, x2 dot v1, so dot product of these two, so clearly you get 3 in the numerator, and v1 dot v1, so square and add, so 1 plus 1 plus 1 plus 1, so you get a 4 here, and 1 1 1, so we subtract and we get this vector. Okay, so that's our v2 vector. You can easily check that v1 dot v2 is exactly 0. Okay, dot product of these two vectors. Now to calculate the third vector v3, we have to find x3, third vector, from here, minus the projection of x3 on v1 minus the projection of x3 on v2. Okay, so we have to solve that equation and find the third vector. Okay, so v3 is x3 minus projection of x3 on v1 minus projection of x3 on v2. Here it is v2. Okay, so here it is corrected, x3 on v2. So x3 minus projection of x3 on v1 minus projection of x3 on v2. And then you can write the x3 vector, calculate these dot products, and write v1 vector, calculate these dot products, write v2 vector, and then subtract or add all these three to write the final vector. Okay, so this third vector, and you can easily check that v1 dot product with this v3 vector is 0, v2 dot product with this v3 vector is 0. Okay, so v1, v2, v3, they will form a orthogonal set that will span the subspace W, and it will form a orthogonal basis. Okay, so this set v1, v2, v3, it forms a orthogonal basis for W. If we have to find the orthonormal basis for W for this, then we just need to divide each of these vector by its length. Okay, so that will become orthonormal basis. So this was about the Gram Schmidt process, and we close this topic for now here. Okay, so keep studying and keep learning. Okay, have a very good time.